That should be good. What I do now is pop the exam in the chat. And then, yeah, we'll crack on with question 5. Okay, f of x is a cubic. G sub a is going to be the function that is the tangent to that cubic at some particular x value. And b is going to be the x-intercept of that tangent. Show that b is equal to all of that. Yeah, so b being the x-intercept, basically it's telling you to find the x-intercept of the tangent, essentially. So we got to imagine what are the key things that come up when it comes to solving tangent lines. And then once we have that tangent line, that's just going to be some sort of linear, right? And so finding the x-intercept of a linear, that's not particularly challenging. The challenge is getting the linear. Couple ways you could go about it. To find any tangent line, you essentially need to know the gradient and a point that exists on that line. So you're trying to find a line that brushes up against the side of this function at x equals a. So the point is really easy. You just got a f of a, right? If it's at x equals a, then the y value that corresponds with that is going to be f of a. So aq minus a. All that's left to do is figure out the gradient at that spot, which we know a few ways of going about. Or I guess one way that works well.
Is it derivative and sub in A?
Yeah, derivative and sub in A is correct. Absolutely. F dash x sub in A, that gets you your gradient. That's pretty much all that's there to talk about for that one, I suppose. So I think at this point I'll just sort of share what I'm hoping will be readable answers. Okay, cool. Yep. So f dash. In fact, how's this? This is quite interesting the way I've organized it. I wrote these well and truly before Newton's method was in the study design. And so what I had done was I said, it's just f dash. This is a gradient point formula, basically. F dash is your gradient, x minus x1, and then is your y1 right there. When you sub in that b value for the x, it's sort of whatever. The main thing there is you get your y-intercept. And so rather than solve the whole linear first and then do y equals 0, you actually end up getting something that looks quite similar to Newton's method. Now it's a bit different, right? You got f on top of f dash rather than the opposite way around, but it's got that sort of similarity to it. Actually, no, is it f on f dash? No, it was f on f dash, wasn't it? That's what Newton's method is. And that should make sense because Newton's method is the repeated solving of x-intercepts of the tangent lines. You don't have to do that, obviously. You could just solve the full linear and then y equals 0 later. But yeah, here's that version. You need f dash. That's just subbing those in. And then we'll, just simplify what you've got until it looks like the exact form that they've got in the question. Take the values of a for which b does not exist. So if b is an x-intercept, then what this is effectively asking us to do is figure out what values of A, so where would I take my tangent to make sure there are no x-intercepts. This is also quite like the Newton's method, but all the way back in 2020. How interesting. They were asking Newton's method questions. What's that, 5 years? No, 4 years before it was in the study design.
Is this plus minus root 3 on 3?
Possibly. Um, so plus minus root 1 on 3, 1 on root 3 on. Yep. Yeah, that's going to be it. Um, how'd you go about that?
Well, if you take the derivative at the turning points, that's where there's gonna be no
Hmm.
x-intercept. So you just make a derivative equal to 0.
Yeah. Yeah, correct. That would be a good way to do it. So you set your derivative equal to 0, so this one equal to 0 and rearrange. The way I had actually done it was to say, hey, if b doesn't exist, that means denominator equals 0. So basically the same thing. It's literally the exact same equation that you're solving, um, but it's a slightly different line of logic to get there. But yeah, that's all good. And the reason why, as you suggested, was yes, if you take a tangent line at a turning point, because it's perfectly horizontal, it'll never touch the x-axis. The nature of the graph of g of a, or g sub a, when b does not exist. That's a pretty ambiguous thing. And so, if I'm not mistaken, I believe they accepted a fair few. Yeah, they were kind of flexible with how you would describe this line. They're basically just asking you to describe what the line would look like. Nature of a tangent line isn't like a key area of study, not like a nature of a stationary point, for instance. So if you could just sort of vaguely describe what this line might be like and look like.
Linear and flat.
Yeah, linear, flat, that's all good. They went with specifically to say horizontal line. That's what they had in the answers. But yeah, stuff like that would be perfectly fine. Um, yeah, state all the values of a for which b equals 1.1. So I guess at this point it's a good reminder that this is a CAS question, or I guess a CAS exam, and you would very easily solve this with CAS. It obviously does, however, require you to have the CAS on hand for one, and two, sub them in, because at this point, or at least up until this point, we didn't really need to do a whole lot.
Negative 0.5052,
Hmm.
0.8084,
Yep,
and 1.3468.
those are all good. Yeah. That would have just been a CAS solve of b equals 1.1, but you've got um, the A version of it. Easy. Graph of f has an x-intercept at 1, 0. State the values of a for which b is between 1 and 1.1, taking special note of the type of inequalities that you have there. I put F has an x-intercept at 1, 0. I don't know how much that matters. I don't really know why that's in there. Oh, I'll say you don't need it, but
The CAS gave me like two different equality like inequalities.
yeah, that's good.
Um, so the first one is like negative 0.5052
Yeah,
and negative 0.5.
yeah, okay.
And the
So
other
it'll,
one was
mhm.
8.084 and then 1.3468
Yeah,
or 3.7, yeah.
yeah, yeah. So just obviously rounding to three decimal places on those, yeah. The only other thing to make sure there is the sets of brackets that are in there. I don't know why I wrote it this way back then, but the sets of brackets you're looking for would be, well, actually, I'll let you maybe say what would the brackets look like, maybe on the first one and then the second one.
On the first one, there'll be like a just a normal x is more than negative 0.505, and then
Yeah,
x is less than or equal to negative 0.5.
yeah, those are good. Yeah, so you could have the sets of inequalities to describe it. The other way would
Yeah.
be the brackets, which would be like a rounded bracket on this one, a square bracket on that one. Yeah.
And then for the other two one, it'll just be like rounded brackets on both of them.
Yeah, two rounded brackets, or as you described earlier, you could have two less than signs basically between the x's. Um, to be super specific, you'd probably also want to have a union symbol between the two, so it's those two in union, and you'd say A is an element of that entire set, or at least something like that. Yeah. Part E. Coordinate B is on the horizontal axis intercept of G sub A. Let G be the. Okay. So you've got two spots that you're taking the tangent line at, such that they are parallel to each other. Yeah, that's not so bad. Um, the good news is whether it's A or B doesn't really matter, because if you think about the initial premise of the starting question at the very least, x equals A just meant some point on the graph. Um, and so x equals A could have been wherever. They've got it here, obviously, to show you a picture. And then x equals B is still just like before the x-intercept of the tangent line. And so we want to figure out like what pair of x values that you would take tangents at such that they become parallel to each other. Here with parallel, we're working with gradients, so derivatives are probably going to be important here. one of the first things you would want to do is get equations that describe the gradient of both of those lines. And then to make them parallel, you would effectively want to equate the two things together. Now, finding the gradient of a tangent line is going to be the same no matter where you take it from. You're still doing derivative at that point. So you're doing, f dash a, f dash b. Both of those work perfectly fine to get your initial gradients. But the problem is you've now got a and b in both things. So although you could equate them, you're trying to solve for a. And so you want to figure out a way to remove the b from the second gradient equation, get it purely in terms of a, and then you can now solve for a to make them parallel. That's a little bit about this here. I can't really. Yeah, there we go. You can get initial equations for both gradients simple by just doing your f dash a, f dash b, and then make them equal to each other because those are gradients. But you want to basically remove the b from the second one in some way, shape, or form and replace it with a's. Yeah, okay. Um, so from where we were talking about, we had our two equations. One of the things you can use is that we've actually got b in terms of a from before. We know that b is equal to 2a cubed over 3a squared minus 1. So, you've got this b thing here, and you're like, could probably just replace it with that. And now you can probably equate it from there. So if we have a look at what that looks like, I've got that here. I wrote something a bit strange here. That's not quite right. I have to fix that. So if we just focus on the cas, basically what I've done is I've replaced this is 3b squared minus 1, but I've replaced the b with 2a cubed over 3a squared minus 1. That's one way to get the gradient for the first thing. And then gradient for the second, so equals 3a squared minus 1. A. And that gets you the string of solutions there. So I don't know what I was on when I wrote this solve. I wrote the right answers there, but put the wrong thing in the solve, I suppose. What you're seeing on the cas is the appropriate set of solutions there. You get your two possible equations, and then use the fact that we know b in terms of a to replace the b with a, and then, well, as we said before, just equate them, solve for a. A can be an element of any real number, so we can use all of these solutions. All of them are valid. Wait, hang on. We do have one final criteria, which is that A cannot equal B. So if we look at the possibilities there, remember A is a point at which you're taking an A is the point at which you're taking a tangent line. If you choose -1 or +1, you've got here or here. Now, the problem with that is those are x-intercepts already. And so there is no next tangent line to take. You would actually have, remember the b value is the x-intercept of the tangent line. And so if you take a tangent line at an x-intercept, then b is equal to a. So we took it at the x equals 1 spot, for instance, on the screen share. B and a would be the same value. Same thing for -1 here. And so for that reason, you would actually just use the plus minus root 515. So slap on the wrist for 2 years ago, Chris. Fair enough, while we have to ignore some of those answers. Anything in there left to clarify? If not, feel free to move on to part F. Show that p of -x equals -p of x for all w. And you've basically got the same equation as before. X cubed plus wx is basically x cubed minus x. You might recognize this relationship. This is just describing the fact that this is called an odd function. Odd functions always have this property. And so proving this is pretty much just a matter of... Oh, go ahead.
Oh, Chris, I thought this is an even function property.
So even is when you've got f of x equals f of -x. That's like quadratics is even.
Oh, okay.
This one is describing, like, if I grab a point down here at y equals whatever this thing is, the y equals -1, I have an opposite reflection, like completely diagonal upwards. What you're describing or looking at here is an odd function. Evens are like parabolas, for instance. Yeah, good to clarify that. But yeah, as for like the way you prove this, you're basically just writing out the expanded versions of each of these. What happens if I replace every x with -x? What happens if I stick a negative out the full thing? Do I get the same thing on both sides? Yes, no. That's the protocol for proving this kind of thing. Which is just that. So just don't forget when you're replacing your x values with -x, anything that's got a power on it, that negative goes inside of the brackets, not on the outside. Although I guess in this case it doesn't really change it, but you do want to be showing that you understand that the substitution would go into the power spot. Yeah, these two things are clearly the same. You would then have some sort of final statement, ... therefore p of -x equals -p of x. All right, now we're going to start getting into more fun stuff. A property of the graphs is that two distinct parallel... Yeah, I mean, that makes sense. So basically this is a property of odd functions, where if you take a tangent line within a certain domain, the opposite tangent line at the next x-intercept, so the this odd property thing, will cause them to be parallel. You can imagine, you can almost just sort of imagine it in your mind, taking tangent lines at different spots. You would see how there's some sort of symmetry. I'm going to restrict how much I talk about this because it's probably going to give away too much. But just sort of imagine different places of taking tangent lines, how you would get some symmetries involved in this scenario. And so, yeah, that's what this is describing, right? You've got the positive version, you've got the negative version. Find all values of w such that the tangent... Oh, this actually went in a different direction than I was thinking it was going to. Find all the values of w such that the tangent to the graph of p at some point for positive So the right-hand side will have an x-intercept at negative t. That shouldn't be bad. Yeah, this wouldn't be too strange. Worded strange, but shouldn't be awful. Oh god, apparently it was. 3% pass rate. Um, yeah, okay. I didn't think it was this bad, at least based on what I was looking at from the way I solved it. Okay, so it's there's a bit more to it than just solving for. Have a go at it, see how far you can get, and then we'll talk through the rest of it. I guess one thing to help clarify your thinking is that we're still finding x-intercepts of tangents. So all the stuff you're already familiar with of how to solve x-intercepts of tangents are going to apply here as well. Furthermore, we've basically just replaced an a with a t, right? Like nothing actually has changed there. So you're literally doing exactly the same thing that you've done before. The only thing that's a bit different here is the point you're subbing in, right? You're not doing what was the point from before? We don't have this b equals thing that we're trying to aim for. We're actually told what it is ahead of time. That changes it slightly changes the order in which you would do things from there. Get you started on that, which would be okay. There we go. So again, I'm using the rearranged version of the gradient point formula. We need p dash of the point, and we need the point. All right, t comma p of t. All this is fairly trivial, right? Just p dash of t instead of p dash of a, and then p of t instead of p of a. You're just going to go through and get your full linear from that. That's what's at the very bottom there. Then to find the x-intercept of a linear, what do we have to do? Same as solving an x-intercept for any function, which would just be y equals 0. Now, the nuance that we have here is that, yes, we know it's y equals 0 because x-intercept, but we're also told just where the x-intercept is. We've got the negative t as well. And so you do exactly that. Replace every t with a negative t. That probably should say negative t. Yeah. Point is, replace all these t's with negative t's, sub in 0, and that will get you this. But that's not the final answer. That's just an equation. W is going to be negative 5t squared. This is what they didn't really say the percentage of people that got it, but they said, quote, some students found this, but were then unable to write down the values of W. You've got to remember, it's not just finding this equation that describes W in terms of t. You have to find all the values of W. Now, I mean, technically, kind of like how a general solution shows you all the possible x-intercepts of the circular function. This technically describes it, but it's not quite what they were looking for. They wanted to have like a domain of W, for instance. What are all the possible W values? I think now that I've highlighted that, it shouldn't be so bad to answer that final bit. All the possible values of W. W is negative 5t squared. That's just a graph. W being negative 5t squared. Same thing as if I said y is equal to negative 5x squared. All the values of W, all the values of y. Basically the same thing. In fact, it's exactly the same thing, just a different letter or sequence of letters. Basically ask you range. Range of W. I think this is just a negative quadratic. What's its range? No one's going to take a stab and try to give me the range of a quadratic. Oh no. Let's get a picture going. Let's plot the graph of W equals negative 5t squared. W is going to be the y-axis, and then t is going to be the x-axis. Excuse me. Now, one thing we've got to highlight is that it does say t has to be greater than 0, so we're going to do x is greater than 0 here. And just looking at the graph, it shoots all the way down. We have a graph of, or a range of 0 to infinity on that one, exclusive of the 0, because we're excluding t equals 0. Yeah, that's what that's what they looked for there, which I imagine was the reason why it was such a low pass rate there. Because this sort of stuff, I mean, we didn't do anything different here than we did in 5A, for instance. We found our tangent line and we subbed in y equals 0, and I guess we're subbing in negative t as opposed to positive t, but whatever. The challenge, I think, that caught a lot of people off guard would have been this thing. The fact that you had to get the range off of it, because it was the possible W values. And clearly it caught me off guard, because I didn't even write it in the answers either. Back maybe 2 years ago, something like that. Okay, now part H is, at least as of now, written not as part of the study design, at least until I give you what the x dash y dash are in this case. That's going to give us x dash equals mx plus h, y dash is equal to ny plus k. Now it's solvable by the study design. So this is your transformation set. M and N can be any real excluding 0. H and K are any real. State any restrictions on those letters, given that the image of P always has the property, oh my god, always has the property that parallel tangents occur at x equals negative t and x equals t for all t greater than, oh, t does not equal 0. Cheeky. So they're giving you a few things to try and clarify your thinking here. The very first time this came up was the show that odd, basically, an odd function. This is also describing an odd function. You got tp of t, negative tp of negative t. Basically, anywhere on the graph that you could choose some a value, the equidistant on the other side, b value, is going to have a parallel tangent. Take it here and here, parallel. If you take it at -1, +1, still parallel. -2, +2, still parallel. And so basically, you've got these transformations, you've got dilation factors, potentially reflections, and translation factors. All that being said, you want to effectively maintain the odd property of it, which is always f of negative b, no, f of, like, it's just this thing, p of negative x equals negative p of x. You want to ensure that whatever you're doing maintains that that property. Those are the goals. Yeah, super tough question. This was a 2% pass rate, so I'm not expecting anyone to really get it. So, or at least, yeah, I guess I should clarify further. It's not necessarily that you want to maintain the odd property of it, because you want to maintain the gradient version of that, which is, if I want to find the gradient at x equals 1, it should be the same as the gradient at -1. Sorry, that's a more accurate version of what you're actually aiming for. So basically, you want to maintain the horizontal symmetry of it. That should clue you in on at least one issue, which is, if you were to translate this graph horizontally in any way possible, suddenly you're running into an issue where it's not centered at the origin anymore. For instance, if I shift it 1 to the right and I do a new x equals 1 and the new x equals -1, it's going to be quite different. Like, here, what can I actually do? If we just get the graph of, what do we actually have here? So it's the graph of P, image of P, W. So I guess it doesn't really matter what W is. So let's just do the very bare bones basics version of it. We'll have the, in fact, I'll define it in the CAS first. Define it as x cubed minus x. That way I can mess around with this a little bit. So like h of x minus h, for instance. Should probably chose it a different letter, whatever. We'll play with horizontal translations. So if we think about the basic version of this, the a equals 0, no horizontal translation. We already have this symmetry where if I take a tangent up here and the tangent on the opposite side, they're going to be the same. As soon as I shift that over, bad. Because now when I take my tangent at -1, it's shooting off like diagonally down, and at -1 it's shooting diagonally up. Bad. So one of the definite things we can say is that we can't have any horizontal translation. So when we think about restrictions on our x dash y dash, we have to have h is 0. It can't be anything else. From there, we would then look at the other possibilities, right? What about vertical translations? Do those ever break? Well, if you play with it a little bit, you'll realize pretty quickly it doesn't actually seem to matter a whole lot because you're still maintaining that horizontal symmetry. Doesn't matter how far up or down you shift this thing at. If I take my tangent at 1, it's going to go like that. At -1, it's also going to go like that. So whether you shift it up or down, because x-axis symmetry is maintained, the vertical translations don't matter. The last things to test would be dilation factors. So you'd come in and you'd do something like 8 times h of x. You would shift it in the both positive and the negative directions. You'll see pretty quickly that nothing's actually changing here. Yes, it's dilating, but you've still got that horizontal symmetry. And if you go negative, you're only flipping it, but you still have that horizontal symmetry. So the last thing to do would be to double check that that's still the case on this version of the dilation. And well, again, you can see nothing's really changing. You can play with this all you like. The horizontal symmetry is still being maintained. Or at least, this odd-like property. So, with that in mind, the only actual restriction here is going to be that we have to have h0. Everything else can be whatever it wants. You can shift it as vertical as you want, you can dilate it however you like, you can reflect it however you like. But as soon as you shift it any amount horizontal, you're in the ship. Yeah, that's all. Anything left to clarify there? Was that a decent enough exploration into why only h was an issue? Okay. Because that's it for the exam. So, if there's any questions, I'll take them. Otherwise, I'll just pull up the next one. 2019. God, we're going to make it all the way to the exam I took. 2018 one. That'd be fun. In fact, the timing of it might actually mean that we finish on 2018, which would be kind of poetic. Because we've only got, what, 2.5 weeks left until the exam. Fun. Alright, tech free. Again, the starting questions are pretty trivial. It's, again, just f dash anti-diff, g dash sub inner point. These are the same questions every single time. I expect you guys will all be fine with doing those. Maybe, maybe this can be a bit weird. You got to make sure you're paying attention to the domains on the hyperbola type graph. Otherwise, you'll get a slightly wrong thing. You shouldn't be using absolute values pretty much ever in methods. So let's start with question 2 instead. Find the rule of F inverse. Right, I should probably drop it in the chat. That'll help. Network disconnected. Can you guys still hear me? Just told me it was network disconnected. Oh, cool. Okay, you can hear me. I, for whatever reason, just can't drop the file in the chat. Fail to send. file could not be sent. Huh. Alright, screenshots it is. That, or obviously just look at the screen share. Yeah, okay, I should have guessed that a screenshot wouldn't work. Cool. Alright, screen share it is. Find the rule of F inverse. Fairly standard question there. Um, you solve these the exact same way every single time. Hmm. You know, that might mean I can't see the chat. If I can't send anything, maybe I can't receive anything. So if there was anything in the chat since 5:50 or so, I apologize, but I did not see it.
We swap the X and Y and solve.
Yeah, swap X and Y and solve.
Hmm.
Absolutely.
I also wanted to ask, is there any like CAS function that does that or no?
Yeah, it's just cas solve. You do solve X equals f of Y, and then comma Y. So I'll do it with a really basic example, just so I don't spend forever typing out the function. H of x is equal to 2x plus 3, nu31 x equals h of y, comma y. And that'll solve like the vast majority of inverses. When it gets to like logs, I think it starts complaining a little bit, but this helps in like pretty much every case. And so yeah, if you do that, it'll do that rearranging for you, whether you give the split fraction or the condensed fraction is whatever. Sweet. The Casio is a lot better at doing this one actually. It's one of the few things the Casio has a benefit or and it does better than the TI Inspire, where it did handle those more complicated log slash exponential inverses. Okay, domain of inverse, again, very standard question. That one you probably couldn't rely too much on the CAS for, because when you're doing a CAS solver, it doesn't really know to... In fact, no, sometimes it does. Sometimes it gives you a warning sign that says something to the effect of domain of input may be larger than range or whatever. I forget the exact terminology that's... Oh, maybe it was there. Did I have it? Nah, I
Is
didn't.
it all real numbers except zero? Because if you sub in zero, then you get a divide by zero error.
Hmm. Yeah, so you're doing that whole domain of inverse is range of original. Um, oh wait, hang on, no, you're doing a different thing then, if you're talking about that. Yeah, yeah, because if you're looking at this, obviously if you have x equals 0, then that's the only one that's bad. So everything else is valid. Yeah, so both ways work. Um, I would still prefer it if you do the whole range of original is domain of inverse, because if this isn't the maximal domain here, if it's a subset of it, then looking at just the inverse function isn't going to help you out too much, because that would assume maximal domain. So I guess to clarify the learning there, uh, you can look at the inverse function exclusively only if maximal domain is applied to it. As soon as there's any restrictions beyond maximal on the original function, then you're in a bit of a shit spot if you're looking at just the inverse because you don't see that information there. But yeah, I mean, look, you can see you can see the marking scheme here. Like these are very standard questions and still, 60% pass rates at best. You guys don't have a whole lot of competition. Okay, this one I need to give you. So this one's going to be x dash equals x plus c, y dash equals y plus d, was it? Yeah, d. So that's the transformation sequence. Find the values of c given that g is the inverse. So the transformation is being applied to f, the original function. Um, and what's basically being described here is, hey, you can apply some sequence of transformations to turn the original function into the inverse function. And it's asking you to figure out what those would be. Depending on which of these forms of the inverse you use, it may be a bit easier or a bit harder to figure out how to go from one to the other. I'd probably stick with the first one, the 1 on 3x plus a third, because all you have to do from there is compare it to f, 1 on 3x minus 1, and then imagine, hey, what do I got to do to make this look like these? First, I'd be going through the sequence of applying the transformation to f. So remember, you start by getting your x and y on their own, and then shoving those in. When you have that, this is now a lot more comparable to that. You can now imagine, hey, what would I have to plug in for C or D, or both, to make it look identical? It can help to look at it in parts. So trying to make the denominators look like each other. And, well, the easiest one is try to make the vertical translations look like each other. That one's a very obvious. D equals a third. This one, slightly trickier, but not too bad. 3x has to be the same as this. You can literally draw up an equation to describe the relationship between them instead of trying to like highball it. And then, yeah, you would just then solve for C. So you get your D equals a third, you get your C equals negative a third. So in order, what was going on there, you had a transformation sequence that you were required to apply. So you start by getting the x and y on their own, sub it into f, and then do a bit of rearranging to make it in the same sort of format as the f inverse. And because you're trying to make f equal to f inverse, well, you just look at each of the individual terms and make them be the same rather. Anything further to clarify? If not, I'll let you enjoy the rest of your day. Thank you.